Hey everyone, welcome to the Cybernetters UNIX Administration course. I'm Andrew Yick, and today we're diving into one of the most important topics in Unix, which is the fundamentals and the file system. So here's what we're covering today. We're going to be covering the Unix command line. We're going to also be covering the file system and directory structure, the file types and management, mounting and disk management, permissions and security, and hard and soft links. We're going to break this all down with real world examples and best practices so you can navigate Unix like a pro. By the end of this session, you'll not only be able to understand the Unix system, but you'll be able to manage it like an administrator. Alright, so let's jump in. So, in the world of Unix and Linux, the command line is everything. So, as an administrator, knowing how to work with commands is what makes you faster, more efficient, and more powerful. Sure, graphical user interfaces exist, but they're great for beginners. But GUI changes all the time and they're not standardized across Unix flavors. And most importantly, they slow you down. So imagine trying to manage hundreds of systems using just a mouse. It's not practical. So that's why mastering the command line is so important. So with the command line, you can do things like that would take a dozen of clicks in a GUI with a single command. You can automate tasks, write scripts, and perform system administration in seconds instead of minutes. This is why Unix has always been so command focused. So you can see this command. Do not run this command. Let's talk about why you should never do. So this command sudo rm-rf slash never, and I mean never, run this command. So let me explain why. So what rm means here, it means removed. So pretty harmless, right? Dash r means recursive. Okay, so what that means is it's deleting directories and everything inside them. Dash f means force, so it won't even ask you for confirmation. Slash means the root of the file system, and which, as we discussed, means everything. So, what happens when you run this? It wipes your entire system, the OS, system files, applications, user data, everything. This actually happened at Google years ago. A single misplaced command led to catastrophic data loss. And trust me, you do not want to be the person who makes that mistake. Running this is like pressing the self-destruct button on your system. Alright, in Unix, commands follow a simple structure. You have the command, flags, and then the operand. So the command is what you want to do, the flag is how it works, and the operand it tells it what to act on. Flags come in two different styles. You have the single character, which is the .x, and then the multiple characters, which is the dash dash list. The longer version is just more readable, but not every command has both. For example, say you want to list file in a directory. ls is the command, dash l is the flag for long format, and slash home is the operand, which is the directory you want to list. So in Unix, everything is a file. Directories, devices like your keyboard and mouse, and even running processes. Unlike Windows, where you have multiple drive letters like C colon or D colon, Unix has one single file system that starts at slash, called the root directory. Everything branches out from there. Even directories are treated as files and they can function as separate file systems when mounted. Once you get this concept, navigating and managing Unix file systems becomes a lot easier. So you can see a picture of the difference between the Windows and the Linux directory structure here. So what I want to do is to focus on one key difference here, how these drives are structured in Windows and Linux. So as I mentioned before, Windows uses multiple drives and each one is separate, meaning these files don't naturally exist under a single structure. Linux also has a single unified file system, which starts at slash. Additional storage, like external devices or external drives or partitions, is mounted under directories like MNT or media. This Like for example, when you're doing let's say you're doing cyber forensics. Like in Windows, analysts can often use tools like DD to create raw disk images of individual drives. In Linux, the same tool can also be used, but since everything is under one structure, it is handled differently. So let's talk about directories in Unix and how they work. There's a key concept here called relative path names, and once you understand this, navigating the system becomes way easier. So let's say I'm working inside Bob's directory, but I want to switch to Mary's directory. Instead of typing the full absolute path in the root, I can take a shortcut by using relative path. So let's say I want to go one level up and one level down into Mary's folder. In Unix, that would look like this: cd dot dot slash Mary. That means you go up one, the double dot means you go up one directory, and then slash Mary means you go down into Mary's directory. So if you're already inside Bob's folder, this is much faster than typing in the full path. So in Unix, we have two different special symbols for navigating directories. The single dot represents the current directory you're in, and the double dot represents the parent directory, one level up. So here is something that I think that can confuse a lot of people. Running executable files in your current directory. So on some Unix systems, if you try to run a program stored in the same folder that you're in, it might not work. Well, why? Because Unix doesn't automatically check the current directory when it's searching for commands. So let's say you have a script called myscript.sh. You type myscript.sh, but the system says command not found. This is because Unix checks a list of predefined directories called the path variable for commands, but your current directory isn't in that list. To fix this, you have to just tell Unix explicitly that the command is in the current directory by adding dot slash before it. So for example, period dot slash my script dot sh. So that way you're saying, hey Unix, look right here, my current directory for this command. And just like this, it runs. So within directories, you also have subdirectories, which is folders inside of other folders. Navigating them which can get very confusing, especially when dealing with long names. But here is where tab completion comes in handy. In Bash, you don't have to type out the full file or directory name. Just type out the first few letters that can uniquely identify the file or folder and then press tab. The shell will automatically complete it for you, or if multiple matches exist, it will show you the list of possible options. Boom, the shell fills in the rest. This saves time, reduces typos, and makes navigation much easier. So in Linux, not all files are the same. There are 6 different types of files, and knowing what they do can help you understand how Unix handles data. So text files are simple files that contain human readable text, often used for configuration settings. Think of files like etc password or shell scripts. And then you have the binary data files, which stores compiled code, images, or system data. You won't read these like a text file, but they contain raw information for programs to use. Linked files are shortcuts or references to other files. If you delete the original file, the link may break, and it depends on how well it was created. You also have the special device files. So instead of storing data, these files represent hardware devices like dev SDA for a hard drive or dev null as a data sink. And then you have the name pipe files, which allow one process to send data to another. So I would like to think of it like a one-way communication channel between programs. You also have the socket files, which work like name pipes but allow network communication. A process on one computer can write to a socket file, while a local process reads from it. And this is how many network services work. So in Linux, file names can be up to 255 characters long and can include letters, numbers, underscores, hyphens, and dots. So what ls does is it lists files and their details. mv moves or renames files. Renaming is like just moving a file to a new name, and then rm deletes files. So some common flags, as we mentioned earlier, is dash F means force, which deletes without confirmation, and then dash R means recursive, so it applies the command to directories and their contents. When working with files, you don't always have to type out every single file name. That's where globing comes in. It lets you match multiple files with using pattern characters, which saves time and effort. So here's how it works. The star matches zero or more characters in a file name, so star.txt grabs all text files. Question mark matches exactly one character in a file name, so file question mark dot text would match file 1.txt but not file 10.txt. AEGH matches one character from a given set A, E, G, or H. A-E matches one character in a range A through E, and exclamation mark A2E matches any character not in the range A through E. So I bet you've probably seen this before, but please be careful. These look similar to regular expressions, but it works differently. So don't mix them up. Globbing is especially useful with commands like ls, cp, or rm when working with multiple files at once. Before you can use a file system, you have to mount it. So think of mounting like plugging in a USB drive. Until the system recognizes it, you can't access the file inside. So the mount point is just a regular directory that just acts as an anchor for the file system. Once mounted, all of the files inside that file system appear inside that directory. So inserting a floppy disk, CD-ROM, or USB doesn't automatically make it accessible. Older systems required manually mounting these devices. So modern users or modern Linux systems have an automounter daemon that detects or mounts removable media automatically. So when you plug in a USB, it appears in slash media or slash mnt without extra steps. So sometimes you need to look inside a file, but not all files are simple text files. Let's talk about how to view and edit both binary and text files in Unix. So extracts, strings extracts and displays only readable text from a binary file, which is useful for checking and hidden images or identifying file contents. OD displays a raw data files raw data in octal by default, but with -x you can view it in hexadecimal, which is great for low file analysis. And then you have the Nano, which is a simple beginner-friendly text editor, which is easy to use but it lacks advanced features. And then you have the V or the Vim editor, which is a powerful editor that every Unix user should learn, in my opinion. And it is a more complex but extremely efficient once mastered. So the diagram that you see here shows what happens before and after mounting a device on Unix. So as you can see, the left diagram shows before mounting, which the USB drive exists physically but isn't accessible because it hadn't been attached to the system yet. But after mounting, the USB is now mounted to /mnt, which makes its content accessible just like any other directory. Alright, let's talk about mounting in Unix. Before you can access a storage device, you need to mount it to a directory. So to mount a device, you use the mount command. You specify the device and where you want to attach it. For example, you can do mount /dev/sdb1/home. This will make the contents of /dev/sdb1 available inside /home. When you're done, you have to unmount it using umount, and no, there's no n inside the command, so be careful. You would use umount and then the mount point as the syntax. For automatic mounting, let's say you want a device to mount automatically at startup. You define it as in etc fstab, which this file tells the system what to mount and where to mount every time the machine boots. Here are some key commands for working with file systems in Unix. So as mentioned before, mount attaches a direct device to a directory so that you can access it. DFHT shows the disk usage with human readable sizes and file system types. LSBLK-FS displays the block devices and their mounted file system. FUSER-U directory checks which user or processes are using a mounted directory, and UMount unmounts a file system to safely remove a device. Let's now talk about monitoring disk space in Unix. So we have two key commands, du and df. Du shows how much space a directory and its contents are using. Du-s summarizes the total size of a directory. Du-h displays sizes in human readable format, and du-i checks the inode usage, which is useful for troubleshooting the file system limits. Now let's talk about DF, which is disk-free. So it monitors the available space on mounted file systems. So df-h displays the storage usage in an easy-to-read format. And always make sure to that the file system is mounted before checking disk space. So file systems can get corrupted, especially after improper shutdowns or hardware failures. Bad blocks unusable disk sectors can also cause problems. Let's talk about how to check and fix them. So, in order to check for errors, fsck is the general file system check tool. But the thing is, you must mount the file system before running it. E2FSK specifically checks the EX2, 3, and 4 file systems. You use -C to scan and mark bad blocks. And then for adjusting the file system parameters, tune to FS modifies the file system settings like checking intervals, and -I can set how often a full file system check is forced. So let's now talk about disk quotas. So think of them as like speed limits for storage. In a multi-user Linux system, you don't want one person filling up the entire hard drive with massive files, right? So that's where quotas come in. So a disk quota is kind of like a storage allowance. It limits how much data a user can store and how many files they can create. This keeps the system fair, and it prevents a single user from taking up all of the available space. So imagine like a shared apartment fridge. Without limits, one person might stuff it full of food, which leaves no room for anyone else. So a quota is like giving each person their own stuff, which ensure everyone gets a fair share. So there are two types of quotas here. The first one is soft limits. So this is like a warning zone. Users can like exceed their limits temporarily, but only for a set period, like a grace period of 7 days. So after that, they must free up space. And then you also have the hard limits, which is the absolute max. Once a user hits their hard limit, they cannot store more data, no exceptions. Think of a soft limit like a hotel checkout time. You get some grace time before you have to leave. Hard limits are like an airline baggage policy. If your bag is over the weight limit, it is not going on the plane. So let's talk about file ownership in Unix. Every file and directory has three ownership levels. So think of it like access roles in a building. So first you have the individual owner, which is the person who created the file. They have the most control over it. So this is like the owner of the apartment. They can decide who can enter and who can't. And then you have the group owner. A file can also belong to a group, which allows multiple users to share access. So it's like a shared workplace where team members can access the same files. And then you have everyone, which refers to all of the users on the system. So if a file has public access, anyone can interact with it. So this is like leaving the door unlocked for anyone to log in, which is not always a good idea. So, why does this matter, you may ask? Each ownership level has its own set of permissions, which decides who can read, write, or execute the file. So, by default, when you create a file, it is owned by you and assigned to your primary group, which follows the SVR4 standard. You can view and modify file ownership to control access. So in order to view ownerships, you can use ls-l to check who owns a file and which group it belongs to. And to change ownership, you can chown user::group file to change both the user and group ownership. And then the chgrp group file, which changes only the group and leaves the user ownership unchanged. Alright, so let's break down file permissions in Unix. Every file and directory has three levels of access control. Who can do what with the file? So the three types are read, denoted by R, which allows the viewing of the file contents or listing of directory files. And then you have the write, which is W, which is allows the modifying of a file or adding, removing files inside a directory. And then you have to execute, which is an X, and it lets you run a file as a program or enter a directory. So think of this as like a house. Read means you can look inside, write means you can rearrange the furniture, and execute means you can walk through the door. So let's understand the ls-l output. So when you run ls-l, you will see something like what I have shown in this slide. So let's break it down. The first character, which is the dash, indicates that it's a file, and D would mean a directory. So dash would mean a file basically. And then the next three, which is the RWX, means the owner's permission, which RWX means user who created the file. And then the next three bits, which is RWX again, which means the group permissions, and RWX meaning the assigned group numbers. And then the last three, which is everyone else's permission. So R-X, which is assigned to all other users basically. So in this case, the owner and the group have full access, RWX, and the others can only read and execute, which is R-X. This means they can run it, but they can't modify it. So what happens if you want to change the permissions? So you would use this command called chmod. So there are two ways to change it, which is symbolic mode and the numeric mode. So the symbolic mode uses U, G, O, and A. U meaning the user, G meaning the group, O meaning others, and A meaning all. So for example, you can see there chmod U plus W, G plus W, O minus X file. So W plus W means add write for the owner and group, and it removes execute minus X for the adder. So for numeric mode, it uses numbers. R means 4, W means 2, and X means 1, and it's summed together. So as you can see, the division of 3 bits as I mentioned earlier, so let's say we use chmod 775 file. So the owner will have 7. That means RWX, so 4 plus 2 plus 1. And then the group, which is denoted by 7, which is the next number, is RWX. So 4 plus 2 plus 1 is 7. And then the others is 5, meaning R-X. So 4 plus 0 plus 1. So that's how it's break down. So think of it like setting a security keypad. So like each number represents a different level access. Setting proper permissions for text files from unauthorized access while allowing collaboration when needed. So some things to note here for file access control. So if a user tries to run a program but it doesn't have execute or X permissions, it will not work. And even if software is properly configured like daemons, it will fail if ownership or permissions aren't set correctly. So What I would do is to always check permissions using ls-l when troubleshooting execution issues. So let's talk about default permissions. So when you create a new file or directory in Unix, it doesn't start with no permissions. It starts with a default permission set. So for new files, it defaults to rw-rw-rw- or 666, meaning it has read and write access for everybody but no execute. And then for new directories, it defaults to rwx, 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 or 777 means full access for everyone, even including execute, since directories must be searchable. So what is UMask? By default, um, files are created wide open, but the system applies UMask to remove certain permissions. So UMask is a special setting that subtracts permissions from the default. So you would use UMask to see the current value and then change it to adjust to default permissions. So for example, let's use UMask 124, which since UMask, remember, works by subtracting the given value from the default permissions. So 124 in binary here would be dash dash x dash w dash r dash dash. So one execute will be removed from others, two write will be removed from group, and four read will be removed from owner. So the final permissions applying UMask 124 would be as shown. So, in simple terms, UMask ensures that new files and directories aren't too open by default, which prevents security risks. So let's talk about the special permissions in Unix. So these are beyond the standard read, write, and execute settings, which provide additional control over files and directories. So when a user runs a file with SUID set, they temporarily inherit the owner's permission. And this is commonly used for system utilities that require elevated packages like password. And so SUID, remember, only applies to files, not directory. So think about like borrowing a VIP pass. You temporarily gain the special access while using that program. And then you have the SGID or set group ID, which is using the numeric value too. So it is different for files and directories. So for files, it runs the file with the SGID bit set that makes the user temporarily inherit the file group ID. And then for directories, any file created inside inherits the group ownership of the directory, which is not the user's primary group. So imagine like a shared workspace where every new file inside automatically belongs to the team instead of just the creator. And then you have the sticky bit using the numeric value 1. So it is historically used for keeping executables in memory for faster performance, and it's now mainly used on directories, which it prevents users from deleting files they don't own, even if they have access to the directory. So one common example is /tmp, where everyone and anyone can write files there, but only the owner can delete them. So think of like blockers at a gym. You can store your stuff, but only you can remove it, even though others can use the space. Alright, so let's now talk about links in Unix. So think of it like a shortcut on your desktop. As you know, you probably have like these apps on your desktop that like directs you to say like Minecraft or whatever. But it doesn't actually contain the file, but it just points to it. So a link is just a pointer to another file or directory. And you can place the link anywhere in the system with any name. And when you edit or manipulate a link, you're just modifying the target file itself. So think about like having multiple doorways to the same room. No matter which one you use, you will just end up in the same place. So some usage examples here are grouping file togethers, which can organize related files without moving them, linking to configuration file, which many system files in Etsy uses links for easier access, and then it also can resolve file name conflicts. Like it can help differentiate software versions like X11 or X11R4, and it simplifies directory structures. So like instead of looking for like a long name like Linux dot two dot six dot zero one zero one, it just creates a link called Linux. So what links in summary does it helps file management, makes it easier, and it reduces duplication while keeping everything accessible. So let's break down the two types of links in Unix, the symbolic links and then the hard links. These are like shortcuts, but they work in different ways. So think of a symbolic link like a Minecraft shortcut on your desktop. It's a pointer to the actual game file, but not the game itself. So if you delete a symlink, the original file is untouched. Symlinks are the most commonly used type of link, especially for directories and shared files. So if you move or delete the target file, the symlink breaks just like a broken shortcut. So a hard link is more like making a copy of the file but without actually duplicating it. So instead of pointing to the file, it points to the same inode or the file ID into the file system. So if you delete the original file, the hard link still works because the data is still there. So imagine you and a friend are sharing the same Google Doc. It doesn't matter who opens the document remains the same. The file only disappears when the last hard link is removed. So in order to create a link, you use the ln to create create links. So for example, you can for symbolic links you can use ln dash s source target, and then for hard link you just remove the dash s to do ln source target. So if you need a quick shortcut, use a symlink, and if you need a true duplicate that won't break, use a hard link. So let's like briefly explain the comparisons between a soft and a hard link. So a soft link can link across file systems and directories, store only the path of the original file, and if the target file is deleted, the link will break. So hard links, remember, is a duplicate reference. So it must be on the same file system and it shares the same endnotes as and permissions as the targets, and even if the original is deleted, the hard link still works. So if you need a flexible shortcut, you use a soft link, and if you want an unbreakable reference, you go with a hard link. Lastly, let's talk about some commands. So, as we mentioned in the last video, pipes send the output of one command to another. ls pipe more, for example, and then redirection, which is denoted by the rightward arrow, which saves the command output to a file instead of displaying it. So for example, you can do ls-l arrow file name. And then for grep, it searches the text inside a file stream. So grep search string file, for example, and then the find locates the file by name or type. So for example, find slash dash type f dash name tar. And then dir cmp compares the two directories and then it highlights the differences. So these commands are important for managing the file and filtering data in Unix efficiently. So that wraps up our deep dive into Unix fundamentals and the file system. We covered everything from file structures to permissions, links, and essential commands. Mastering these concepts is important to becoming proficient in Unix administration. So now, if you want to test your knowledge, head over to cybernetters.net. We got quizzes for each topic to help reinforce what you learned today. If you found this video helpful, please make sure to like, subscribe, and hit the notification bell so you don't miss out on future lessons. Thanks for watching, and as always, stay secure and keep learning with Cybernetters. See you in the next one.